There's a specific kind of fatigue that doesn't come from sleep deprivation. It doesn't show up after a late night or a missed meal. It shows up on a Tuesday afternoon when nothing unusual has happened. The coffee wore off around noon. By 2, the mind slows, not dramatically, but enough. The body continues functioning. Work gets done, but there's a quality to the effort that wasn't there at 28. Something costs more than it used to. Most people who experience this don't report it to a doctor. There's no acute symptom, no clear diagnosis. It registers instead as a general sense that recovery takes longer, that energy is harder to sustain across a full day, that mornings feel less decisive than they once did. What's notable is how consistent this pattern is across demographics. It doesn't correlate cleanly with fitness level, sleep quality, or stress, though all of those matter. It appears across people who exercise regularly and people who don't, across high-stress and low-stress environments, across dietary patterns. The consistency of the pattern points away from lifestyle variables and towards something more foundational, something occurring at the level of how the body generates and regulates energy itself. The response to this kind of fatigue tends to follow a recognizable sequence. Caffeine consumption increases, this is almost universal, not as a deliberate strategy, but as a gradual adaptation. The second cup becomes routine, the afternoon cup gets added, the timing shifts earlier. For a period, this works, but the ceiling on caffeine's effectiveness doesn't scale with demand, and the quality of the energy it produces, reactive, sometimes anxious, dependent on timing, begins to feel like a poor substitute for something more stable. Sleep becomes a project. There's an entire infrastructure of behavioral and environmental adjustments that emerge around this point. Earlier bedtimes, consistent wake times, screen reduction before sleep, temperature optimization. Again, this helps, up to a point, but people who implement all of it correctly often report that their sleep improves without their energy fully recovering. The two, it turns out, are related, but not equivalent. Diet gets revised. Sugar is reduced, protein increases, meal timing is restructured. For many people, these adjustments produce modest improvements, but not resolution. The underlying pattern persists. What each of these attempts shares is a focus on input management, on modifying the raw materials or conditions the body works with. What they generally don't address is what happens to those inputs after they arrive. The relevant mechanism here involves the mitochondria, the structures within cells responsible for converting available fuel into usable cellular energy in the form of adenosine triphosphate, or ATP. Mitochondrial function doesn't remain static across a lifespan. Research in cellular biology has documented a gradual decline in both mitochondrial density, the number of these structures per cell, and mitochondrial efficiency, how effectively each one performs its conversion function. This process begins earlier than most people expect, with measurable changes appearing in the mid-30s, and accumulates progressively over subsequent decades. The significance of this is structural. It means that even when inputs are adequate, when nutrition is sound, sleep is sufficient, and lifestyle variables are well managed, the downstream conversion process may be operating below its earlier baseline. The raw material is present, the processing capacity has changed. This also explains why lifestyle interventions, while genuinely useful, tend to produce diminishing returns in addressing energy regulation specifically. They optimize what enters the system. They have limited influence over what happens inside the cell. There's an additional layer to this. Certain molecular compounds that support mitochondrial function, including NAD+, a coenzyme involved in energy metabolism, also decline with age. NAD+ participates directly in the cellular processes by which mitochondria convert fuel to ATP. Its reduction over time compounds the efficiency issue, creating a situation where both the hardware and one of its key operating compounds are simultaneously declining. The result is a system that continues to function, sometimes well, but that operates with a narrower margin than it once did. Small disruptions have larger effects. Recovery takes longer. Sustained output requires more conscious effort. The research around mitochondrial decline and NAD+ reduction has produced a parallel field of inquiry into whether these processes can be influenced and through what means. The conventional assumption has been that mitochondrial decline is a fixed feature of aging, observable, measurable, and essentially unmodifiable beyond what exercise can achieve. Exercise does, in fact, support mitochondrial biogenesis, the process by which new mitochondria are generated. This is one of the more well-documented physiological benefits of regular aerobic activity. But the conversation has expanded. Over the past decade, a body of research, conducted primarily in academic and clinical settings, has examined whether specific molecular precursors can be introduced to support NAD+ levels. NMN, or nicotinamide mononucleotide, and NR, nicotinamide riboside, are among the compounds that have received the most sustained attention in this context. Both function as upstream precursors in the pathway through which NAD+ is synthesized within cells. The findings have been variable, and it would be inaccurate to characterize the science as settled, but the mechanistic rationale is coherent, and the direction of the research, including several human trials, has been sufficient to move these compounds from theoretical interest to active commercial development and ongoing clinical investigation. This represents a meaningful shift. The question of how to address energy regulation after 35 now has more than one category of answer. Within this field, a category of products has emerged specifically targeting NAD+ precursor supplementation. These are not positioned as stimulants or short-term energy products in the conventional sense. Their mechanism of action is cellular, and their proposed effects, where supported by research, operate on a longer timeline than caffeine or sugar. NMN-based supplements, in particular, have moved from early-stage research contexts into consumer availability. Formulations vary in delivery method, dosage, and adjunct ingredients. Some include compounds intended to support absorption or to address related cellular processes simultaneously. The landscape is not uniform. Regulatory frameworks around these supplements differ by region, and the quality and transparency of available products vary considerably. Independent verification of ingredient purity and claimed dosages has become a differentiating factor within the category. For individuals who have addressed the conventional variables, sleep, nutrition, exercise, and are specifically interested in the mitochondrial and NAD+ dimension of energy regulation, this category represents a legitimate area of investigation. What the research on post-35 energy regulation consistently points towards is a distinction between symptoms and mechanism. The symptoms, the slower mornings, the narrower window of sustained output, the longer recovery, are real and widely reported. The mechanisms underlying them are increasingly well characterized: mitochondrial efficiency, NAD+ availability, cellular energy metabolism. Understanding that distinction changes what questions are worth asking. The relevant question is no longer only how to supply more energy to a system, but whether the system's capacity to process that energy has changed, and whether that capacity can be supported. That's a different kind of problem, and it has a different kind of answer.